Hi, I am Lakshmikant Tiwari. In this lesson, I am going to teach you how you can use linear and logistic regression coefficients with lasso and ridge regression or L1 and L2 regularization for a feature selection in a machine learning. So in this lesson, first I'll tell you about what is linear regression, and then I'll tell you what are the basic assumptions which we need to make during the training and the testing of our model. Then I'll tell you what is the lasso and ridge regularization or lasso and ridge regression and L1 and L2 regularization. Then we talk about the lasso regularizations are regression, and then we talk about the source of errors, the type of errors, then bias and the variance trade-off. Then we talk about how we can select a tuning parameter, the lambda, and then we talk about the ridge regression or L2 regularization, and then we talk about the differences between L1 and the L2 regularization. And then finally we start working on the Titanic dataset, and I have taken a detailed documentation on Titanic dataset. If you see my previous lesson, so I have taken the Titanic dataset very detailed. You can go ahead and watch it on my channel Logistic Regression with the Titanic dataset. And after that I'll do some pre-processing for a dataset, and then we will remove I'll remove the null values, and then finally I'll convert the string values into a numerical value so that I can apply a machine learning algorithms. After that, I'll first talk about the linear regression, how you can select your features with the help of the coefficients of the linear regression. Then in the second section, I'll talk about how you can select the features with the logistic regression and L1 regularization, and then finally how you can select a feature with the help of the L2 regularization and the logistic regression. Then I'll show you the best accuracy we have got into by using logistic regression and L1 regularization, and that was 82.8%. And if you have been working with the Titanic dataset, you can understand that 82.8% accuracy is quite good, and this is the one of the fantastic and the best accuracy in the Titanic dataset. Okay, so without wasting time, let's go ahead and start a brand new lesson on the use of linear and logistic regression coefficients with the lasso and ridge regression for a feature selection in machine learning. Now we need to first understand what is a linear regression. Linear regression is a straightforward approach for predicting a quantitative response y on the basis of different predictor variables of x1 and x2 etc. It assumes that there is a linear relationship between the x and y. That's mean with some linear multiplications and addition or the subtraction, the y can be predicted based on the input features, and those inputs are the x1, x2. So we can say a x vector, and these beta 0, beta 1 and beta p are the coefficients of a linear regression. And if you see here the epsilon is the error, and later in this lesson I'll show you how many types of the error. It's not just single type of the error, there are different type of the error which get introduces into a model when we train our or test our model. While working with the linear regression, we have to make some basic assumptions, and those basic assumptions are like we can predict y by using a linear combination of the input vectors, and feature space x should have a Gaussian distribution, and features are not correlated with each other. That means there should not be any multicollinearity. That means these features are not correlated in between or themselves, and features are in the same scale. That's mean these features should be into the same scale. That's mean we need to do normalization or standardization to bring these features into a same scale. Since in this lesson we are going to learn how we can do the feature selection based on the coefficients of a linear and the logistic regression, and these coefficients of a linear and the logistic regressions we are going to calculate with the Lasso and Ridge regularization. Now let's go and understand what is the regularization. Regularization is a technique to discourage the complexity of a model. It does by the penalizing the loss function, and this helps to solve the overfitting problem into our machine learning model, and ultimately it improves the accuracy and reduce the complexity of the model, and it increase the interpretability of the model. Regularization, as I told earlier, that it adds a penalty and different parameters of a model to reduce the freedom of the model. That's mean to reduce the complexity of a model. Hence, the model will be less likely to fit the noise of the training data, and it will improve the generalization ability of the model. Later in this lesson, I'll show you what is the generalization of a model. There are basically three types of the regularization: L1 regularization, L2 regularization, and L1 and L2 regularization. So in general, L1 regularization, also known as Lasso regularization, and L2 regularization, also known as Ridge regularization, and these are also known as Lasso regression and Ridge regression as well. The key difference between these techniques is that Lasso shrinks the coefficients which are less important to the zero. That means with the Lasso regularization we can remove a few features, but in the Ridge regression it doesn't reduce the coefficients to zero, but it reduces the regression coefficients, and with the reduction of the regression coefficients we can identify which feature have a importance in a final prediction. That's mean, for example, if let's say if you need to predict the y, and if beta 1 is greater than beta p, that's mean the importance of this x1 is more as comparison to xp, because beta 1 is larger than beta p. That's mean the overall the effect of these multiplication of beta 1 with the x1 is larger than the effect of this one. So in the same way, by seeing these coefficients, if coefficient is large, then we can identify that which feature have a most importance and which feature doesn't. Now let's go ahead and learn what is a Lasso regularization. There are three sources of error. That means there are three types by which error introduced into our testing or training model, and those errors are a noise actually which cannot be reduced, and then we have a bias and the variance in the form of the noise. So with this, what we can do, we can't do anything with the noise, but somehow we can remove a bias and the variance. But there is some trade-off in between bias and the variance. We can't remove bias and the variance both together. If we start reducing the bias, then the variance start increasing. We have to find out some sweet spot and where the generalization error is minimum actually. Okay, I mean the total error, generalization error, irreducible error plus bias and the plus variance. So that is some sweet spot. We need to find out that sweet spot, and based on the model complexity, as we increase the model complexity, our bias starts decreasing but the variance start increasing. But after a certain limit we can't increase the model complexity. We have to find out some sweet spot, and in the same way we need to identify the best possible combination of a bias and variance. And now if you see here in the Lasso regularization, for example, let's say you have the model of the regression, and now let's go ahead and replace this beta with the W0, W1 and the WP. That's mean the beta with the W, and these W, let's say the coefficients of regression, that's the regression coefficients. So this is the actual error, okay. And then what we do in the regularization, actually in the Lasso regularization adds the penalty equivalent to the absolute sum of the regression coefficients. Okay, and earlier in this presentation we had seen the regression coefficients are the beta. Whether we can say the beta or the w, though it's the same thing. Moreover, I just want to say here is that, so this in the Lasso regularization, and this is the error function, loss function. So what we do, we add lambda, where is lambda is regularization coefficients or optimization coefficients, and multiplied by the absolute sum of regression coefficients. So in this way, what we do, we add some penalty into a loss function. Now we need to find out the some sweet spot where where the error should be, the generalization error should be the less, and overall in general model should perform better. And with this, if you see, and if you see the coefficients of the regression coefficients, so here it is shown on the housing pricing data set. You see, after adding the regularization, and then you see the coefficients of few the parameters are becoming 0. Okay, that's mean what it is saying, that there are few features which actually doesn't doesn't put much information to identify the output. So this is how works this L1 regularization. And now let's go ahead and see how we can choose the best lambda. Okay, this lambda, how we can choose the best lambda. For example, we need to make a assumption here. Let's say we have a sufficient amount of the data, and in that we can break our data, we can split our data into the training set, validation set, and testing set. In the training set, we fit our model, and then we get here our regression coefficient, and with the regularization, and then we test our model performance on a validation set, and if there is something problem, or if accuracy is not increasing, or anything wrong is there, then it validate on the model, validate on the validation set. If there is something wrong, then it changes the parameter, then goes back to the training set and do the optimization on the validation set. Then finally do the generalization, generalized testing on the test set. Okay, so this is how we choose the best lambda during our regularization. Now let's go ahead and learn what is the ridge regression or ridge regularization. Ridge regularization is also known as L2 regularization, which adds penalty equal to the sum of the squared value of the coefficients, as we can see here. And this lambda is the tuning parameter, or you can say optimization parameter. Okay, and the W is a regression coefficients, and it adds this penalty in a loss function by the square of a regression coefficients multiplied by the tuning parameter. So in this L2 regularization, what we can say here, if lambda is large, very large, in that case the bias will be the high. That's when we are introducing too much penalty, and the model is too much generalized. In that case, the bias will be high, but the variance will be the low. But if lambda is small, then in that case, now we are increasing the complexity of our model. If lambda is small, complexity of model will increase. In that case, our during the testing, the model will try to fit each and every points. In that case, the bias will be the low, but the variance will be the high, and that will be the not good in the term of the generalization error. So what we do, we find out the some optimized value of the lambda by tuning this parameter, and then we can identify that, okay, this is the lambda tuning parameter, the value of the tuning parameter, which is performing perfect in our case. Okay, and you can say also this lambda is a strength of regularization actually. Okay, the larger the lambda, the larger the regularization strength. So the L2 regularization will force the parameters to be relatively small, but L2 regularization doesn't force the parameter to equal to 0. That's mean in L2 regularization we don't reduce the we don't reduce the feature set by saying that okay the coefficients are the 0, but in fact we find out that okay the regression coefficients of these and that features are good, like here these, and the regression coefficients of these features are the high. That's mean these features are most important, and the coefficients for which features are the low, then those features are not important in predicting the final output. So this is how we select the feature. Now after this theory, I'm just gonna tell you what is the difference between L1 and L2 regularization. L1 regularization, it penalizes sum of absolute value of weights. L1 has a sparse solution, it has a multiple solution as well, it has a built-in feature selection as well, and it is robust to outliers, and L1 generates the model that are simple and interpretable, that cannot learn complex patterns. But in L2 regularization, this regularization penalizes sum of a square weights. It has a non-sparse solution, and it has one solution, and it has no feature selection actually, but we can do the feature selection based on the coefficients of the regression, and it is not the robust to the outliers, and it gives a better predictions when the output variable is a function of all input features in a linear space. And L2 regularization is able to learn a complex data pattern, but you see L1 is not able to learn a complex data pattern. Okay, so this is all about the in theory. Now let's go ahead and I'll tell you how we can work with the dataset, and in this I'm gonna load the Titanic dataset. But before that, what we are gonna do here, we are going to import NumPy as a NP, Pandas as a PT, Seaborn as a SNS, Matplotlib.py plot as a PLT. SQL and model selection, import train test split, and then the random forest classifier, select key based and percentile, and then accuracy score. So let's run the cell. Then we are going to import the linear regression and the logistic regression and the select from model. Okay, and then we are going to load here the Titanic dataset. And one thing I should also tell you that you can download this working file from video description. I have given the link there, and you can also visit my channel KGP Talkie to see other videos as well. And now let's go ahead and see the head of this Titanic dataset. I have been covering this Titanic dataset in many other the videos as well. I have described this Titanic datasets, and I have done a lot of the data exploratory analysis. Then you can go ahead and see my logistic regression video, in which I have taken the Titanic dataset and done a very in-depth analysis of this dataset. So let's go ahead and check if there is null values, and of course there are so many null values. And now we are gonna drop the columns which have large null values, and there we have dropped here the age and the deck. And now after this we are gonna drop the NA values for the rows like embarked, town, and embarked. Now let's go ahead and check if there is null values. It says that there is no null values present into the data set. Now let's go ahead and select only few selected the features. Those features are the passenger class, sex, siblings, parents, child, embark, who, and the alone. And now let's go ahead and see the head of this data. Now one thing you can see here, the values are into the string, but in the while training the model, the string value doesn't work. Then what we need to do here, we need to change these string values into a numerical data, and those numerical data we can convert by this string this map function. So we need to create here a dictionary. Sex is equal to the male with 0 and female with 1, and then apply this map function on the data sex, and then save this into the sex. And now you see here, now you can see sorry, I think we had run it the 2 times. Okay, so with this, now you see here, the earlier we have sex male, female, 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 male, and now you have 0 for a male and female, you know, the 1 for a female. So this string value has been converted into the numerical value on which machine learning algorithms can work. And similarly, let's go ahead and convert this embarked as well with the help of the mapping function. And similarly, we can convert this who with the help of the mapping function, where man will be replaced with the 0, woman with 1, child with 2. And similarly, we can do with the alone as well. Now let's go ahead and see few lines of our data, and in that, now you can see all the values has been converted into the numerical values. Let's go ahead and read the data into x vector, which will be the serving as a input is feature space, and the y is a target. And now let's go ahead and see the the shape of x and the y vectors. So it has 889 rows and 7 vectors, 7 features. And let's go ahead and do train and the test split. Now after this, there is a true actual estimation of coefficients of linear regression. So the first we will start doing coefficient estimation by using linear regression. Then after that, I'll show you how we can do model selection. So you know, we have also imported the select from model. Let's go ahead and create that selector, and I'll tell you about more this select from model. If you press shift and the double tab, you will get detailed documentation about select from model. There you can see, there it takes first input parameter as a estimator, then it takes the threshold, etc, etc. And in the estimator, the base estimator from which the transformation is built, and then finally we can select dot transform, and then finally we can do the feature selection. Moreover, what I want to tell you here is that I'm gonna pass estimator, linear regression estimator. Since linear regression works on a matrix, matrix estimation, so it doesn't work on the gradient descent. That's why it doesn't have any regularization in a linear regression. So in a linear regression, it is just simple linear regression, and then finally it will calculate the coefficients, and based on the coefficients we can find out higher the coefficients, better the effect of the feature on the output. Let's go ahead and fit this model. We can do with the cell dot fit. Okay, cell dot fit, and in this cell dot fit we are gonna pass here x train, and then we need to also pass here y train. So with this, now you can see here we have trained our model there, and let's go ahead and see the coefficients of this model. We can get with the selector plus get support. With this get support, it says that with the selector, it has selected these features only. Okay, and these features are the first 2 features. That's mean those first 2 features are the passenger class and the sex, and then finally the second last, that is the who. So with this select from model, what it do, it calculates the coefficients of the linear regression, and then select from model by default the threshold which I was talking earlier, that so this threshold is actually by default, if you see in a detailed documentation. So this threshold by default is a mean of the coefficients. So what it does, it calculates the regression coefficients, and then it find out the mean of the total calculated regression coefficients, and then it selects only those features which have the regression coefficients greater than the mean. How we can do that, actually, let me tell you. Let's go ahead and do estimator coefficients. With this, now you see these are the coefficients, and let's go ahead and get the mean of this actually. Okay, then you will understand what I'm talking about. So here we have a mean, and its mean is 0.02. okay, so it selects all those it selects all those which are actually the greater than which are the greater than those the mean values. So with this it might get confusing for you a little, but it is actually how it is working. Actually it takes the absolute value of mean. So we need to do ABS in p.abs, and then now you calculate here. It says that the mean of this absolute value, which we can actually put here into the mean variable, it says that the mean is 0.137. And now let's go ahead and calculate the absolute value of the selector. Then we can do the ABS with this selector. Now you see here, this value is greater than this value is greater than this value, and similarly now you can see here with the true. So it is gonna select the first two feature where you can see the values of the coefficients are greater than this, but the other coefficients for the other variables features is low, only the second last, which is 0.2385. and now you see here it is selected the second last. So this is how this select from model select the coefficients. So now what we can do, and similarly we can calculate the features which we are gonna select. The features is equal to x underscore train dot columns. Okay, and then we have select estimated coefficients. With this not estimated, this should be the get support actually. Now with this, if we print this feature, then you will see we with this the p class, sex and the who. So these are the three most important features which we have selected by the coefficients, evaluating the coefficients of the linear regression. Perfect. Now let's go ahead and get the transform version of X train. I mean the training and the testing dataset, which we can select just these three classes, p class, sex and who. So let's go ahead and do that as well. We have X train and reg, that's the regression, and then with the selector we can apply there the transform function on X train data, and then similarly we have here X test underscore ridge, and similarly we have here the selector dot transform function, and we can apply that on the X underscore test. Finally we have got the training and the testing data set, that is the converted, which have just got selected with these three features, okay, which we can actually get with the xreg dot head. Sorry, it doesn't have actually the head, but anyway if you see the shape of this, now it is just a 3. Okay, perfect. So now let's go ahead and implement the random forest function, and then we will do the training of this data set with the random forest, and then we will evaluate the accuracy of the data set. So with this, as usual we need to write a function for a random forest. So here we have a random, then forest. In that we are gonna pass here x train, and then we need to pass here x test, then we need to pass here y train, and then finally y test. And then we need to bring we need to implement the classifier, which is the CLF random classifier, which takes the number of estimators, which we are gonna pass here 100, and it takes the random state. I'm gonna pass a 0 so that it should take you should get a same result if you pass same random state. And n job equal to the -1 says that it can utilize all the cores while training or fitting our model, which you can do with clf.fit. Okay, and we have x train, and then we have y train. So this is the how it is working. Then here we have y pred is equal to clf dot predict x underscore test. So in this way we can get here the accuracy, accuracy score, and in that we need to pass here the true value of y, which is the y test, and the predicted value of y, which is y pred. So let's go ahead and run this, and we can do with the run random forest, and there we need to pass here x train reg and then x test reg, and we have here y train, and then finally we have y test. It says that we have got the fantastic accuracy, which is 82.39%. Now let's go ahead and check this accuracy on the original data set, and that is the x train and x test. Okay, so on the original data set, I think yes, we have the almost the same accuracy actually. And if you check here the shape of the x train, you see here it has 7 features, but x train reg have just 3 features. Okay, perfect. So now here you can understand that how we can reduce the feature space from the 7 features to just 3 features actually. Okay, now let's go ahead and do the logistic use logistic regression coefficients with L1 and L2 regularization to select the feature. Logistic regression coefficient with L1 regularization. Okay, perfect. So what we need to do here, same way as we did earlier, we need to write here cell is equal to the select from model, that's mean the selector we are gonna implement, and now we are going to pass here estimator a logistic regression. Since a logistic regression can take the regularization parameter, which we can pass with the penalty, by default it's the L2 penalty, otherwise we can also pass L1 and L2. Now let's go ahead and pass these parameters. So the first we are gonna pass here the penalty. The penalty says that we are gonna pass L1, and then the C means the strength of the regularization, which I'm gonna do. Initially I'm gonna just pass here the 10. That's mean it's not pretty much strength, since C is inverse of the strength. Now in the documentation you can see there the C means it is inverse of the regularization. That's mean a smaller value specify the stronger, but here we are passing a larger value for regularization. Larger means it will not do any regularization overall. And the solver for this, which I'm gonna pass, that is live linear. Okay, perfect. So we have got the selector. Let's go ahead and fit the model with the data set, which we have original data set, x train and the test. Once it is done, then let's go ahead and get the features which it has selected. Now let's run this, and I think something is wrong here. Let's go ahead and see. It says that the input shape is bad. I do not know why this input shape is bad actually. Sorry, yes, that should be the sorry, y train. Okay, so with this now you can see it has not selected any it has not removed any of the features, because the C is quite high. That's mean there is almost no regularization. Let's go ahead and reduce it to the 1. In case of the 1, which is default value, there is no regularization. Let's go ahead and reduce it 0.5. In this you can see no regularization. Let's go ahead and reduce it to the 0.4. No regularization. Let's go ahead reduce it to the 0.3. Now in this case, do you get anything? No, we don't get. So with this, what we are going to do with the 0.1, now with 0.1 we have removed the last feature. This one says that okay, this was the least important feature, and that we can understand with the coefficients of the coefficients of the regression coefficients. Okay, so it has removed here the false one, that means the last, and and here they still I'm gonna reduce it from 0.1 to 0.05. Now if I do this, now I can see here it has selected the 4 parameters. Okay, and those four features are first 3 features and then second last. Now you can see here it is almost going as we got here into our linear regression. Okay, so we can do these things in the same way. Now let's go ahead and calculate the coefficients of these. Okay, so with the coefficients, how we can do with the cell and then estimator, then here we have a coefficients. So these are the coefficients. So here we have a first 3 coefficients which is the first 3 features whose coefficients are not 0, that means those will be into our transform data, and the second or last is also not a 0, and the other coefficients now you can see here are the 0. So this is the beauty of the L1 regularization. In L1 regularization, the features which is not important, it makes the coefficients of that feature equal to the 0. That means ultimately that will be removed from the feature space. Now let's go ahead and get the transform data set, which we can get with the x train underscore L1 is equal to cell dot transform, and then we have here x underscore train, and then similarly we have x underscore test underscore L1, that's is equal to select dot transform, and then here we have x underscore test. So with this we have got the transform data set with the L1 regularization. Now let's go ahead and run this data and try to get the accuracy, how much accuracy we will be getting with this. Okay, so we need to pass x train L1 and x test L1, then we need to pass here y train, then finally y test. So this is how now you see with this we have got the 82.77% accuracy, and the earlier we had 82.39%. So this is how the regularization of the L1 and with the help of the coefficients of the linear regression, we can select the features which are most important in a final selection. Even though if you have seen the previously we had selected all the features and we had got the accuracy of the 82.4%, but here we have got the accuracy of 82.8%. so there is a gain of the accuracy. Okay, and if you have a large feature set, let's say the 300-400 feature set, and then with the help of the logistic regression coefficients and L1 regularization, you can really reduce your feature space from large feature dimensions to a smaller dimensions, which will actually make your system faster, and that might also increase your accuracy, the model's accuracy. Now let's go ahead and implement the L2 regularization. Okay, so for L2 regularization, what we are going to do, the same thing which we did here. So just copy it, you can press here the C on your keyboard and just paste it here with the V on keyboard. Okay, so with this what we get here, the selector, we have got the selector, select from model, logistic regression, penalty is equal to the L1, C वगैरह, sorry, the penalty is equal to the L1, C is equal to 0.05, but we need to just change this penalty from L1 to L2, and other things will be the same. Now let's go ahead and select with the L2. Now with the L2 you can find out here that we have again got the same feature which we have got with the linear regression. And now let's go ahead and see the coefficients of regression, and then we can transform our data set, and then finally we can evaluate the accuracy. And with this, now we can understand that we have selected the same features as we had selected into our linear regression, and we will of course get the same accuracy. Moreover, the long story in the short, in this lesson I have shown you how you can select a feature by using a coefficient of a linear regression and logistic regression with L1 and L2 regularization. If you have a large feature set and you want to reduce the training time and of course the dimensionality of your feature, then I think the feature selection methods with these techniques is definitely gonna help you a lot. Okay, thank you so much for watching this video. Please do not forget to like this video and subscribe this channel. Stay tuned with me to get more videos. Bye bye. Have a nice day.